Hey, good morning, everybody. So today we begin our review for your tests. Friday today and Monday, we will both having review days, and then your test will be on Tuesday. So you know what happens when we have a review? That means you get a big fat review packet to go ahead and look over and practice for your test. So your test will be very much like this. Make sure you can do everything on here. If you can do this, you can do that. In fact, the test should be easier than the review. Although if there's anything that you don't know how to do, that's what's probably today and Monday, specifically Monday, you know, a lot of time today to look things over, but you got the whole weekend to play with it and mess around with it. And then you can come back on Monday and see what you don't know how to do. Of course, your two assignments are also due on Monday, playing catch up from the snow days. So make sure you're working on those. And we're going to go ahead and start to review. So let's do it. Here we go. All right, so based on, let's see here, based on these two functions, three functions, f, g, and h, determine the following functions along with their domains. So it's been a very long time since we've done this stuff. Let's make sure we got this kind of under our belt. All right, so what's this kind of thing mean when they have a parenthesis with a bunch of letters and then of x? That just means you do those operations on the functions, correct, of x. So it can be really complicated. I put 3 this time, ooh. But it just means you're going to take f plus g and then minus h. So that's all there is to it. F is this thing, so here's F. And then it says plus G, so I'm adding on G, which is X plus this weird root thing. And then it says minus H, so I have to subtract function H. Now be careful when you subtract functions, especially if they got more than one thing. Make sure you subtract the whole function, which means you need to put that function in parentheses right there. So that's what that function would look like. Any questions over the notation? I don't think so. We could clean up just a little bit. I don't know. I can put these x's together. There's not really a lot to do. Let's distribute this out. That'd be a negative x cubed. Would you agree if we put that in there? Negative x cubed. I see an x squared. I'm going to try and write things in the right order too. Cubes and squares and stuff. There are 3 x's, 2x and an x, so 3x. And there are some numbers. Let's see. I had a -1. That's a positive 1 over there, right? I also got another positive 1. So that's a grand total of positive 2. And we've pretty much cleaned up everything except for that weird, funky root. That's kind of an awkward freak in here. So there you go. Something like that, all simplified. And then that's kind of all I got to do. They also want you to find the domain. So the two things you have to remember about domains, and this is kind of your review in itself, domains, there are 2 things you got to watch out for. Number 1, can't divide by 0. Always got to worry about that. And the second thing to worry about is no negative numbers under even roots. If you have a negative under an even root, like a -1 under a square root, it turns all imaginary, and that's no good. So this one, if you scan it, that's all you got to do the rest of your life. Anybody asks you about domain, just think about these 2 things. Any division here? I don't see any division. You see any division? No. But I do see an even root. This is a square root, correct? So the stuff under it cannot be negative. That means the stuff under it, which is x minus 5, right? Can't be negative, so it could be greater than 0, that's positive, or it could actually equal 0. So that's what you always do. Please write down that inequality right there. If you see an even root, that's what you go do. You set the stuff underneath of it, set it greater than or equal to 0. And that means that x must be greater than or equal to 5. So the only numbers allowed to plug into this particular equation are everything from 5 on to infinity. So this one's domain, bracket 5 to infinity. Watch out for even roots, okay? Even roots, you do have to take a half a second, set the stuff under it greater than or equal to 0, and figure out where that is, and that's the only place it's defined. If you did go graph this thing, you'd see it only exists from 5 on. Anything to the left of 5 would just not even exist and be a big problem. So there's that one. Any questions over the domain or anything like that? All right, let's move right along then. Number 2, what are they asking you to do on this one? They are asking you to do H with a circle of G. Now, what does that mean? That's a composition. The way you say that is H composed with G. Remember what you do with this stuff? You take the function on the right, and you literally plug it into the function on the left. So let's see what we can do. G is this thing right here, correct? So I'm going to take this thing and plug it into h. So everywhere I see x and h, which is only one right here, correct? I'm going to replace it with g. So this thing was cubed. So now I have what g was cubed, and then minus 1. Notice it looks exactly like h. The only difference is it's not x, it's g. So you plugged it in right there, and you're good. That's it, right? Nothing really else to do with that. Domain. For the same exact reason as before, this has an even root in it. So you do the exact same logic, and you'd see that the domain is from 5 to infinity again. Same exact thing. X minus 5 must be greater than or equal to 0. And that's all there is to that. Questions over the composition stuff. We plug one side of the other. All right. Well, lastly today, the third one is just find H inverse. So what is the inverse? Remember, that's what that -1 power means. It's not a power. When it's attached to a letter like that, it means it's an inverse. The thing that undoes this function. So how do you find an inverse? Here's your steps. First, you call your function y. Remember this thing at all? Then you're going to switch your x's and your y's. As soon as you switch your x's and your y's, you are now talking about inverses. So you literally change the letters. Every y becomes x, and every x becomes y. Now we're talking about the inverse. You have to solve for y. That is what the inverse is. So you just got to add 1 over. And then we have a cube. So how do we undo a cube? Now we know the whole unit that to undo a cube, we do a cube root. So I need to do a cube root of this stuff. That is what y is. And y represents now the inverse. So there's my answer. H inverse of x is apparently the cubic root of x plus h. And its domain, well, let's see. Do we have any division? I don't see any division. No, don't need to worry about that. I only need to worry about negatives under even roots. Is that an even root? No, that's not a root. So I don't need to worry about anything. So actually, every number is okay. Everything from -infinity to infinity is just fine on this particular graph. That was like 2 sections in one of a review right there. That all makes sense? Pretty old, so I kind of thought we'd forgot a lot of it, but if you got that, that's pretty darn good. So let's go ahead and do our LGs, and then we will continue to review. Oh, yeah. Starting to review for the test today. That's a lot of what the front of the unit was about. It wasn't even about roots. It was just about adding functions, composing them, checking for inverses, finding inverses, things like that. And it might seem like that had nothing to do with the rest of the unit, but the rest of the unit then started saying, okay, how do you undo squares and cubes? Well, the inverses of those are roots and things like that. So it did become kind of relevant to the rest of this unit. Yes, you may. Just got to hand out your review assignment. That's a good thing. 6.7. That'll be due on Tuesday when your test is. You will not have much time in class to work, so you really need to be hitting homework hard outside of here and come with questions. That's what we got time for. We got time for questions. All right, so lots of stuff. Okay, first of all, this slide is a lie. What do you have on your plate? 6.5, correct? If you don't have that done, 6.5 from before the snow, 2 weeks ago or whatever, that is going to be due on Monday. That 166 is also a lie. Do you do any of those problems? No, you just get online, you do the ones on reveal, and that'll also be due on Monday. And like we just said, 6.7 now, their due dates are starting to match what we're actually doing. Will be on Tuesday because that's when your test is. All right, here we go. Unit 6 is a quick review. We're going to do half of it today and half of it on Monday. Let's see what we can do today. Start off talking about just operations on functions. Sounds like you guys got a pretty good handle on that already. One more time, look at the notation. They say f plus g or something like that. They mean take function f plus function g, right? They say f dot g, just a normal dot, not an open dot like this one. Any dot means to multiply, right? So f times g, you take them times each other. And with division, same thing. Just watch out for dividing by what? I just harped on it. Don't divide by 0. Yeah, so if you ever have any division, scan it real quick and make sure you don't divide by 0. And if it does, take it out of the domain. For example, this one on the board, if you solve 2x minus 4 equals 0, you'd get x equals 2. So you can't have x be 2. You can have everything from -infinity to everything from 2 to infinity, but you'd have to skip over that 2 right there. So again, that box down there is gold. Okay, rest of your life, domain. That's all you got to worry about. Any function the rest of your life. Am I dividing by 0? Are there negatives under my even roots? If so, then I have to watch out for that. We just did a composition too. A composition is where you put a function inside of another function. It's functions built on functions, like a chain of functions, one after another. And you do it right to left. Okay, so if it says f composed with g, that's what that little circle means. Open circle means composed. You take the function on the right, g, and you substitute into function f for every single x. And the letters are meaningless. If I said h composed with I, you take I and put it into h and things like that. That's about it for section 6.1. Any questions over that? Cool. Well, let's do a problem then. I always like to do that with you guys too. So 1 through 5 is anything like that. Do you see anything on your review assignment 1 through 5 that you'd like to do? Or would you like me to just go on and shut up and you guys do it on yourself later? It's totally up to you. I would pick one. Yeah. Let's do number 3. All right. Take a look at number 3. It says g divided by f. So let's take a look at this thing. Number 3 on your review assignment. Good one to pick. Because it's got division. We got to worry about division. We can't be divided by 0. So if you look at the top of your review assignment, it says what g and f are. G is, by definition, says it is x cubed minus 8. So there's g on top. And on bottom is f, which is 5x plus 10. Now, there's not really anything I expect you to do with division besides that. Okay, if you want to go do long division and try to simplify it, be my guest, but that's not required. You told me you understand what this means, right? This divided by this divided by this, we're okay. Probably the only thing that's going to be tricky is the domain. So let's see, do you see the even roots? I don't see any even roots, right? Don't need to worry about that. But I do see division. So the thing on the bottom, 5x plus 10, better not be 0. This is the only real work that it takes on this kind of a problem. And if you go see when the bottom is 0 and you move the 10 over and you divide by 5, it looks like -2 is a problem. So you can't plug in -2 because the whole bottom would then equal 0, right? So that's not good. Every number but -2 is fine. So my domain is going to be everything from -infinity until -2, but I got to put a parenthesis on it and skip over it because -2 is no good. But then everything after -2, so everything from -2 to infinity is also just fine. So that's it. And that's probably about how long one of those problems should take you. So that's should not be insanely strenuous, but be careful with all the little things, minus, negatives, and multiplication and combined like terms. I mean, it does take a little bit of work. So good question on that. Cool. All right, let's get back to the other stuff then. So the next section, 6.2, is actually about finding inverses. Now, this is a confusing section. Had like restricting domains and all this kind of other nonsense on it. I did not put anything like that on your test, okay? There's nothing on there about restricting domains or weird things like that. So you're off the hook on that. But what you do need to know, what an inverse is, it undoes a function, okay? It goes the other way. A function takes an input and spits something out. The inverse takes that output and gives you back the input kind of thing. And as we just kind of reviewed in the warm-up, here are the steps to find an inverse. 2 things also you should understand graphically. Always good to understand what's going on graphically with things. No matter what function you ever have, it doesn't matter how funky it gets, something like this. If that's your function, you can always take your function and flip it over this magic line, y equals x, and as soon as you do, whatever that thing is, that is your inverse function right there. So it's very important to understand that graphically when you flip it over this line, that's your inverse right there. And what happens in your work when you flip something over this line is all the x's and y's get changed. So if this was coordinate 5, 1, for example, on the inverse, you'd have 1, 5. The x's and the y's get flipped. So algebraically, how you're going to always find an inverse is you are going to switch your x's and your y's. Down there is that procedure we just did in the warm-up. Whatever the function is, call it y, right? Switch your x's and your y's and solve for y, and then you found the inverse. Nothing too tricky in that section. In fact, that's really all I wanted to hit on section 6.2, except for the fact that if you do have 2 random functions given to you, f and g, and I didn't even put this on your review, so you don't have to worry about it too much. But if you compose them, so if you take f composed with g, or you take g composed with f, and you get out x, if that happens, maybe there is 1 or 2 problems on here. I don't know. Let me see real quick. Yeah, there are some problems like this. So you better know this. if you have two functions given to you, you want to check and see if they are inverses, compose them. If you get out x, then they're inverses. If you don't get out x, then they're not inverses. And that's really all there is to that right there. So let's take a break. 6 through 9 is really just finding inverses. And 10 through 13 is checking to see if two functions are inverses, like we just discussed. So you want to see any of them done? 6 through 9, just finding an inverse? They're pretty straightforward, but we could do one if you want. Which one? 6 through 9? Those are just ones where you find an inverse. You don't do anything else. You just find an inverse. 9, let's do some 9. Here we go. Write her down. Going to number 9. So as x to the 99th, a little bit intimidating. Ooh. So this function is x to the 99th plus 3. Well, it doesn't really matter what power I give you. The process is the same to find an inverse. Your steps are call f of x y. So I did that. The only reason we're doing that is so I can switch our x's and our y's right there, which is exactly what we're going to do next. So this is still the original function, but as soon as you change all the letters around, now it's the inverse. And my job is to solve for y. Don't let the 99 scare you. Let's get this thing by itself. How about we subtract the 3? We had something very similar in the warm-up. We had y cubed, and we didn't do it with a cube root, correct? Well, if I got a y to the 99th, I'm going to undo that with a 99th root. That's what roots do. They get rid of exponents. So no matter what it is right there, that's what it is. And that's what y is. But y now stands for the inverse. So on that slot where they say f inverse of x, there it is. It's the 99th root of x minus 3. Make sense on that? And then 10 through 13 is just checking if you if I give you two random functions, can you compose them and check to see if they are inverses or not? You want to see one of those done or not? Number 11, that does look kind of tricky. It's got some fractions. All right, here we go with number 11. So they give you two random functions, f of x, 2x minus 4. They also give you another function, g of x, which is 1/2 x plus 2. My job is to algebraically figure out if these are inverses. That means you need to compose them. You need to do both. You need to do f composed with g, and you also need to do g composed with f and see if you get out x. So let's see if we do. Again, this means I'm taking function g and plugging it into function f. So I'm going to take this thing and plug it in for this x right here. So it's going to be 2 times what I'm plugging in, which is this whole thing, 1/2 x plus 2. So there's 2 times what I'm plugging in. And then, of course, it has a minus 4 on the end. Any questions over that composition right there? Nothing? Well, is that x? That's the question. Does that simplify to x? I don't know. It's a little early to tell. I got a 2 times something. Why don't we distribute that in and see what happens? 2 times 1/2. Well, that's just 1, right? So I got 1x. That's promising because I want an x. But then you got 2 times 2, which is 4. But then what's on the end? A minus 4. So they cancel out. So this is just x. That's what I want. Okay, it's looking like they're inverses. But you should always go both ways and check. Don't just do f composed with g, do the other one as well. G composed with f. Let's see if I take function f and plug it into function g and get out the same thing. Well, here's function g. It says 1/2, and what I'm plugging in to x is f, which is 2x minus 4. So there's g with the x replaced with what f is. And again, if you distribute things out, 1/2 times 2 is 1. So I got an x again. 1/2 times -4 is -2, which plus 2 is nothing. So I just got x. So both are x, and that's the work to justify their inverses. So you can circle yes now. Make sure you're showing me some work, though, okay? It's not going to count to just circle a yes or a no and leave the work blank. You have to justify it. You can't just take a 50-50 shot and hope you get the right answer. You have to show work. to verify that that's actually how it works. All right, any questions over those sections at all? We're zipping right along. I like this. All right, so moving right along, now we're starting to talk about nth roots and rational exponents. That's the stuff where we spent the most time on, simplifying roots. Remember, that's what a root symbol looks like on the board right there, up at the top left, the little tiny superscript up there that represents what the root is, called the index, but you don't need to know that. And here's the main thing I want you guys to remember. If you take an even root, what do you need to put on your stuff on the outside? Absolute values, right? If you take an odd root, you don't need to worry about that. But the key thing is that fourth roots will do things raised to the fourth power. Eighth roots will undo things raised to the eighth power. So your job is to hunt for things that are buried inside of your root that can be raised to whatever power you're doing. So if you had a sixth root, you're going to be hunting for things inside that are raised to the sixth power. And maybe there's some leftovers, maybe there's not. I will have this table up for you during your test. You're welcome. You're welcome to look at your notes as well, correct? You're going to need it, right? There's going to be a lot of numbers from this table. There's going to be a lot of 16s and 125s and 27s floating around, so you better have this table pretty handy to simplify some roots and things like that. You should also know what a fractional exponent means. It means a root. So if something raises to the 1/3 power, that means it's a cubic root. They raise to the 1/8 power, it means an eighth root, and so on and so forth. Right here, you can expand this idea. Okay, what if you have any fraction as your exponent? Not just a half or a third, but what about 5/6 or something like that? Well, remember, the number on the bottom of your fraction represents the root, correct? And the number on top is just a regular old exponent. So if that happens to come up, which I don't think comes up a lot in your work, but if it does, that's something to keep in mind right there. All right, let's try to see, well, what else we got to do? Let's review the graphing part too before we go on, because this is really where I want to stop today. What do the graphs of radical functions look like? Well, we should know that all even roots look like square roots, look like something like this. So fourth roots, and sixth roots, and eighth roots, etc. They all look like this. We're familiar with that shape? Hopefully so. And by default, all their domains are from 0 to infinity. And all their ranges are also from 0 up to infinity. Now, there might be some shifts and stretches and things like that. So some jerk came along and said, oh, how about this graph? -6th root of x plus 2 minus 3 or something like that. How in the world would you figure out what that looks like? Well, I want you to tell me what's different between any of these and this. Tell me one difference you see. There's a negative in front, right? What happens when you put a negative in front of your function? To the function, it's a vertical reflection, right? Oh, it's not x, it's x plus 2. What happens when you add things to x's? It's a horizontal shift. But which way? Horizontal or backwards? To the left. And the -3 on the end is a vertical shift down, right? So I would think that this particular graph, what do we say? We have 2 to the left, right? 3 down. That right there is where my vertex would be. And since it's negative, it's not going to open up. It's going to open down. So this particular graph would look something like that right there. And then you can read the domain very easily, right? The domain is from -2 to infinity. And the range is from -infinity up to -3 right there. So I don't want to spend forever talking about shifts and stretches. They're important. What's another way you could do that if you don't want to think about stretches and shifts? Remember, the vertex is where the inside is equal to 0. Remember that trick? So that's a little easier. And it's pretty easy to spot this is -2. And this is down 3, right? So you just go 2 over and 3 down, same answer as you got before. But you do got to scan for negatives because negatives flip things and change the shape. Make sense? Okay. Then you also have odd roots, so on and so forth. And they all kind of look like this right here. They zip right up and they go right through the origin and something like that. Now, the same exact logic to figure out where this goes. If I said, oh, what's the 7th root of x plus 8 minus 3 look like? Well, you do the same thing. When's the inside equal to 0 at -8, right? And this moves it down 3, right? So what's that tell me? That tells me where the center is. So this one tells me where the vertex is, and the same logic for this one tells me where the center is. So this one would be at -8, down 3, and that's where the center would be, right? Do you see any negatives in front? No, any negatives there? Nope, no flipping. So it's going to look exactly like what you would think it looks like normally, kind of goes up something like that, and you're good. You also have your graphing calculator, correct? So you should go check it and graph it also to make sure that you're actually doing it right, but your brain should be kind of firing things off about that quickly because that's what we've been studying all unit. It should be pretty familiar to us. Good? I don't think I got much else to say about graphs of these things. There's inequalities too. I didn't even put that on your test. Don't worry about that. You don't have to worry about it. Graph is, shade above, below. It's kind of dumb things. You don't have to worry about that. That's about it. Now let's look at our reviews assignment and see if there's any more questions. That's where I want to stop for today. So 14 and 15 are about graphing things. So is 16 and 17. So I figure we should do one graphing one. Is that probably a good idea? So anything 14 through 17, anything looks scary? Which one? 17. 17 does look scary. All right, 17 is an even root. It's got a bunch of funky things in here. I love to do this to you. Someday, I hope that when I put a weird number in there that you will not freak out. You'll do the same thing you would do if it was a normal number. In fact, maybe we should do it with a normal number. This is probably scaring you. So here's your problem. What scares you? I know what scares you. It's got this root inside this other root, right? And you're like freaking out. Well, just to show you that you shouldn't freak out, I'm going to replace that number with something else. How about 7? If I gave you that, would that be as scary? Okay, it's no different just because I'm using a weird number here. It's just square root of 5. It's just a number, right? This is just a number. Don't let me freak you out when I use a different number. Now, I'll tell you what, let's do this one. Okay, if you're in a bind, do a simpler version and then switch it back to the more complicated one. So from this one, let's see what it would look like. Well, it's a fourth root, so it's an even root, correct? There's a negative in front of that. What's that do to my graph? That flips it vertically, correct? So I'm thinking this looks kind of like this one opening down. Mental note is kind of look like that, opening down. Can you tell me where the vertex is by looking at it? What makes that 0? -7, and that's down 2, right? So this graph would be at -7, 1, 2, 3, 4, 5, 6, 7, -2, and it would open down, right? What's different between this one and that one? It's not 7, it's square root of 5. So what's the only difference going to be? This isn't going to be at -7. It's going to be at negative square root of 5. Yeah, it's the same exact logic. So this one right here, again, if you look at this fresh, when's the inside equal to 0? That's what you're trying to find, right? Well, if x plus square root of 5 is 0, then that happens at, like we just said, negative square root of 5. So just because it's a weird number doesn't mean that the rules are any different. So you go find where negative square root of 5 is. It's a little past 2, and then down 2. So something like this, and then opening down. That'd be actually my answer for this one. This is one of those ones where I'm also checking to see if you're actually thinking as opposed to just putting in your calculator. You could try to go find where this point is. Your calculator's going to say it's like -2.23 or something like that. I don't want -2.23. Where is that exactly? Negative square root of 5, right? So that's kind of the point. So domain and range to finish it up. Any questions over the logic on any of this? It's okay if you got questions. All right. Domain is therefore from negative square root of 5 to infinity, correct? Exists all the way from negative square root of 5 to infinity. And the range is from negative infinity up to -2. So really, over the years, I'm trying to break you of the habit of when I put the word pi or square root of 5 or something weird, you don't think all the rules are different. It's the exact same rules before. This was x plus 5. You'd say x plus 5 equals 0, right? And x would be -5. Just because I say square root of 5 doesn't mean the logic is any different at all. Yes? That was the root, wasn't it? So all that told me was that it's an even root. So that told me that it looked like that. So that kind of got me started on the shape of it. Had it been an odd root, I'd be doing the same thing with an odd kind of thing. Good stuff. Good questions. Good questions. That one was a little tricky. Look over that one, okay? Make sure you understand all this going to the test. And then lastly, let's do anything 18 through 27. They're all simplifying roots, which is probably a big skill we should at least do one problem on. And heck, if you want to even do two, I'd let that slide because this is important right here. Anything 18 through 27, there's a lot of them. I figure I knew that. I could sense that one coming. 27's got a fraction. So let's look at that one. Oh, yeah, that is kind of tricky. 27. It's a cubic root of something. Oh, yeah, this is a beast. Look at this thing. Dang. Yeah, this is kind of mean. This is testing a lot of your stuff. First off, does anybody remember what a negative exponent means? That's kind of what I'm checking right here. Anybody know what a negative exponent means? That is right. Very good. So I am just checking right off the bat that if you see a negative exponent, you know it really goes on the bottom as a positive exponent. So before I'm even going to start cleaning up this root, let's just worry about that. There was a y squared on bottom because there was a y to the negative second on the top. So that's what I'm checking right there. Negative powers mean it goes on the bottom. And before I even get to any more crazy, I can put some y's together. I see a y to the 7th and a y squared together. What's that? That's y to the 9th, isn't it? So let's call that y to the 9th. So this part right here, I'm not even checking your knowledge of roots. I'm just checking your knowledge of Algebra 1 exponent rules, honestly. Good thing you knew that. And if you didn't know that, then go remember what a negative exponent means. Okay, that's a little cleaner. Now we can't avoid it anymore. Let's talk about this root. It's a cube root, correct? Negatives. Can you have a negative under an odd root? The answer is yes. In fact, if you have a negative under an odd root, it just comes out in front. So there's another thing to remember. Lots of things to remember. If you have a negative under an odd root, it can just come out in front. Because remember, if you take an odd number and multiply by itself, or a negative number, multiply by itself an odd amount of times, it's still negative. Now the rest is just normal business, okay? That was a lot of heavy theory. First off, I want to review before I go on. Are we clear on the negative exponent means it's on the bottom? Okay. Secondly, if you see a negative under an odd root, what can you do? Bring it out in front, okay? Those are the two tricks to this problem. The rest is just the same crap we always do. We got a cubic root of something, so I want to write these as cubes. Could you write x to the 9th as something cubed? Remember what the trick is? Take the exponent divided by the root, correct? And 9 divided by 3 is just 3. So yeah, I can write x to the 9th as something cubed. There's a 125. I wonder why 125. Anybody got that table? It's something. Was that intentional? Something cubed, and it is 5. 5 cubed is 125. And similarly, we can write y to the 9th as something cubed in the exact same way. We can call that y cubed cubed. Y to the 9th is y cubed cubed. Any questions over that? And the whole reason we're writing these things as cubes is because the cubic root and the cubes will cancel. So finally, in the end, we have a negative. We have a negative. On the top of my fraction, the cubic root and this cube will cancel. And that just leaves me with x cubed. On the bottom, the cubic root and the 5 cubed will cancel, leaving me with just a 5. And the cubic root of y cubed cubed will just be y cubed. No need to worry about absolute values on this one. You're doing an odd root, third root. So you just simplify things the best you can. And that's all you got to worry about. So that one was a very mean one, yes. But study it. That's the whole point of this, right? Ask me the mean ones. I do some mean ones. You figure out some. You study it. And then when the test comes, you are just fine. So there's the point of that. Good question on that. Anything else you want to do? Feeling generous. Anything else? 18 through 27. One more that maybe looks really scary. They're all kind of scary. What about like 26 or something with a, can you rationalize from the conjugate thing? Can you do that? Want to do 26? Let's do 26. That was one that we didn't spend a ton of time on, so I kind of understand why we forget it. 26, it's not that bad. I just want to make sure we remember how to do it. Here, your job is to rationalize the denominator, clean things up as much as possible. This is not considered clean because you got roots on the bottom, okay? You don't want roots on the bottom. And if you ever see a root plus a root or root minus a root, you should think I should multiply the top and bottom by the conjugate of the bottom. So what's conjugate mean? Well, it's the exact same thing with the sign in the middle changed, correct? So this one, we're going to multiply top and bottom by square root of 8 plus square root of 3. And like any fraction, you can't just do it to the bottom. You got to do the top and the bottom. When you multiply straight across, really there's not going to be a lot that happens on the top. 5 times both of these is just 5 times both of them. So in fact, kind of distributing that 5 in is kind of pointless, but hey, it's fine. The top will be some weird garbled mess. That's not the point. The point is the bottom should be pretty. These conjugates should turn into a nice clean number when we distribute it out, and let's see if it does. Square root of 8 times square root of 8. You should know what that is. What's square root of 8 times square root of 8? 8. Check. And then you're going to have 8 times square root of 3, correct? But the next thing is you're going to have a negative square root of 8 times square root of 3. So what do those do? They always cancel out with conjugates. That's kind of pimp. And then on the end, you're going to have a negative square root of 3 times square root of 3, which is just negative 3. So if you did that distribution, you should get a nice thing like 8 minus 3. Hey, that's interesting. It worked out like that. I just made up some nonsense. I can't believe the bottom had a 5 in it because look what's on top also. Bunch of 5s. So we can go one step farther and divide all this. In fact, if you divide everything on the top by 5, you just get square root of 8 plus square root of 3. And if you divide everything on bottom by 5, you just have 1. And I'm not going to write divide by 1 because that's stupid. So actually, it turns out to be just this, nice and clean. Square root of 8 plus square root of 3. And that's about it. You do a very similar thing on 23. See, 23, it's also got like a root minus a root. Just because it's x in it doesn't mean it's any different. You do a conjugate on that as well. Rest, a bunch of simplifying. So I'm going to let you struggle on that, okay? When we come back on Monday, very short review to finish things up, okay? We're just going to talk about solving equations. So the bulk of the review has been done now. You will have a decent chunk on Monday to ask questions, but worry about 6.5 and 6.6. Get those off your plate. Be working on this steadily, and on Monday, we will tidy it all up. Have a good day, everybody.